Okay, hello everyone. In this video, we are going to discuss classical theory of electronic polarizability. Okay, so let's start. So first of all, we are going to define that electronic polarizability. So here, electronic polarizability, that is your alpha subscript of E, is nothing but the displacement of an electron, a single electron with respect to nucleus per unit applied external electric field. So here you can see that in your figure 1a is a unpolarized atom. Suppose we are consider that single electron, when we are going to apply the DC electric field upon this unpolarized atom, then the electronic clouds are going to be displaced with respect to central nucleus, which is positive charge, by a distance x, which is the so called atomic polarizability that we know. But each and every electron, this electron, how much distance displaced with its original position, that is called as your electronic polarization. Corresponding polarizability will be called as the electronic polarizability. Suppose you just consider this electron, suppose this electron. So this electron is at this situation. Whenever we are going to apply a electric field, suppose this electron has been displaced a distance, suppose this distance here. Suppose initially will be at here, and it is displaced by a small distance, this one, and this distance multiplied with suppose this distance is your small d. Okay, so this distance d multiplied with a electronic charge of a single electron, this is nothing but called as your electronic polarization. Corresponding polarizability, that means per unit applied electric field, will be called as your electronic polarizability. Okay, that we are going to derive, and what will be its value, that we are going to derive, and how it will be related with susceptibility, and again susceptibility, how it will related with a dielectric constant, that belongs to a real part of the dielectric constant and imaginary part of the dielectric constant, that we are going to discuss in this video. Okay, so for the simplicity we have been considered here a unpolarized atom. Whenever we are going to apply a DC, then the electronic cloud, or the net, or the your you can say uh, uh, center of gravity of negative charge and positive charge are going to be displaced a distance, which is called as your atomic polarization, that we know. Okay, so when DC field will be applied on a unpolarized atom, which is represented in figure 1a, then it will be polarized in a particular direction, represented in figure 1b, this one, along single direction. However, when external electric field AC will be applied on an unpolarized atom, then two times I have been written mistakenly, so then it will be polarized along both the directions. You can refer the figure 1 C and 1D. Here mistakenly written. Wait. So here first of all I have to correct it, that this one, and figure this one, figure C and figure D, you can refer the polarization due to AC electric field, that is this figure and this figure. This is your figure C and D. Okay, or it can be said that the polarization will be oscillated about the mean position. Here you can see when a positive half cycle is going to be entered or going to be applied through this parallel plate capacitor, suppose this will be polarization, that means positive net positive charge and net negative charge separated by a distance. When negative half cycle is going to be applied through this parallel plate, then it will alter its polarization, that means this side will be your net positive and this side will be net negative, because we are applying the AC electric field. If this AC will be continuously applied on this polarization, then the polarization will be oscillate about its mean position. So same thing, it has been written that uh, it can also be said that the polarization will oscillate about a mean position, and the frequency of oscillating polarization is equal to a frequency of applied AC. Okay, so hence an applied AC field, in an applied AC field, the atom behaves as a harmonic oscillator, because here you can see for half cycle this side is positive, this side is negative, then another half cycle positive, negative, and this will be oscillate alternatively. So we can say that it is harmonic, behaves as like a harmonic oscillator. So for continuous oscillation, AC act as your external force. So here I am going to give one example. Suppose this is your spring, balance spring, and attached with mass, and if I will be drag it and leave this, then it will oscillate about the mean position, and if it will oscillate continuously, I have to apply the continuous force. So if this oscillation, electronic oscillation will be continued, then the external force will be nothing but your applied AC. Okay, so hence atom will be executed the forced harmonic oscillation. The force is given by the external AC field. So first, here we are going to consider, we have to consider the oscillation of a single electron, then all electrons per unit volume we are going to consider. So as we discussed that if a single electron will be oscillate with the applied AC field, then it will be called as your forced harmonic oscillation, and we know that the general equation of forced harmonic equation for forced harmonic oscillation will be in this form. So here if we are going to consider mass of the electron is m, and electron is oscillating along x-axis as shown in figure C and D, then the forced harmonic oscillation of a single electron can be written with the help of this second order differential equation, that is your m d square x by dt square, m beta dx by dt, m omega 0 square x into equal to e into E0 into e to the power I omega t. So this is your AC field, and this E0 is nothing but amplitude of applied AC, and this E is nothing but your electronic charge, and as this is the electric field, we are applying oscillating electric field, and we know that force is nothing but E into applied electric field. So here applied electric field is a AC field, so it is represented by E naught into the I omega t, and this is the charge of electron will be equal to this much. This is the typical second order differential equation of a forced harmonic oscillator, and let this is your equation number 1. And here x is the instantaneous displacement of an electron, m is the mass what we discussed, and omega 0 is nothing but your natural frequency of the electron. Omega here frequency of the applied AC, E is the charge of the electron, E is the amplitude of the AC field, B the damping effect, which is the value is this one, that you have to remember. We are not going to detail about this. This is the damping effect, and this value is depends upon natural frequency, permeability, charge of the electron, mass, and here C is the speed of the light. Okay, now as it is a second order differential equation, we can expect the solution of this second order equation, second order differential equation will be in this form, that is your x equal to x naught e to the I omega t. Let this is your equation number 2, and if you are going to take the derivative with respect to t of this x and double derivative of this displacement with respect to t, then we can found I omega x dx by dt. Let this is your equation number 3. D square x by dt square will be equal to minus omega square x. Let this is your equation number 4. Now we are going to substitute these values 2, 3 and 4 in your equation number 1. Here is the second order derivative, first and x. Simple, we are going to substitute, then we are going to found this one. Okay, so here you can see, here I am going to remove the lines that you can easily take the screenshot for your note. Okay, okay, so you can take the screenshot for your note. So for the 6 mark question, you have to write from here, more or less you can omit from this write up, and this figure you have to do. Okay, so actually the from here, from the equation number 1 you have to write, and the definition you have to write, and in between that whatever the write up I have been written, then you can more or less you can omit in your exam. Okay, equation number 1, sorry, this will be the equation we found whenever we are going to substitute 2, 3, 4 in your equation number 1, and here mx common factor common in these all three terms then can be taken outside, and we found this one equal to e into e naught e to the I omega t. So that implies x will be equal to, here this side will be e by m and into e naught e to the I omega t by this much minus omega square into plus I beta omega plus omega 0 square. Okay, but in general uh, polarizability, if we are going to consider, is nothing but induced single dipole moment. Suppose we are going to consider this is the dipole moment, single dipole moment, that means two different charges are separated by a distance d, then the dipole moment will be nothing but your q into d. And polarizability, that we know that if we are going to polarizability, nothing but p is equal to polarizability into applied electric field, and polarizability equal to p by e, that we know, that means dipole moment per unit applied electric field, that we know. So polarizability in general, we know that the induced single dipole moment, that is your charge into displacement per unit applied electric field. So in this case, electronic polarizability of a single electron, suppose we are going to consider this electron has been displaced from this original position, this one, suppose this is the original position of this electron and it is displaced by a distance, suppose x. Okay, so if it is displaced, we can expect that here hole is formed, or here one positive charge has been induced. So due to this displacement of this particular electron, the dipole moment will be how much, e into x, and per unit applied electric field, that means applied electric field is your nothing but this one, E0 e to the I omega t. So in this case, electron polarizability is nothing but single electron displaced by a distance x. So here uh, x is nothing but the displacement, this small displacement for this electron. Suppose we are going to consider this x, or any electron you consider, suppose this electron has been displaced from here to here x distance. So electron displacement will be nothing but charge of the electron displacement divided by applied electric field, that is nothing but is your E0 e to the power I omega t, which is your alpha e. Okay, okay, take the screenshot for your uh, note. Okay, okay, so we found alpha e equal to, here e by e not e to the I omega t, as such I have been written, instead of x I substituted this value. Okay, so here e into e is your e square, and here E0 e to the I omega t, E0 e to the I omega t got cancelled, and we found this is your equation number 5. Okay, okay. So now we are going to go for the next slide, that now. So here we found that equation number 5 represents the electronic polarizability of a single electron, right? But in case of polarization, or if we are going to consider a large amount of polarization, then we have to consider the number of electrons. So now consider n number of electrons present in one volume, in unit volume. So here capital N is the number of electrons we have been considered present per unit volume. Then dielectric susceptibility Xi E will be is nothing but n into alpha E, n into alpha E. So here n is nothing but number of electrons present per unit volume, and alpha is nothing but electronic polarizability, right? So how it is, here you can see that we previously know that Xi E is nothing but P by epsilon 0 E in SI unit and CGS unit P by E. Okay, so here you can see that P is nothing but n number of electrons or number of charged particles, number of atoms or number of electrons, here in this case number of electrons into individual dipole moment or single dipole moment P. This is the capital P, that means polarization per unit volume. And we know that single dipole moment is nothing but polarizability into applied electric field. That means polarizability, if here we are going to consider atomic electronic polarizability, then alpha E into E means your AC electric field. So alpha E will be nothing but P by E, right? So here we can write N into instead of P, sorry, okay. So here I can write instead of small p, we can write this alpha into E. Okay, alpha into E. Okay, so now here you can see that this capital P, that is nothing but polarization per unit volume, is nothing but N alpha E into E. So here you just substitute this value N alpha E into E. So here E got cancelled, and we found N alpha E by epsilon 0 in your SI unit, which is nothing but called as the susceptibility, or in CGS unit this is nothing but N alpha E. So here susceptibility is nothing but your N into alpha E. So these things you have to remember, that susceptibility is nothing but your polarization per unit volume per unit applied electric field. That things already we have been discussed in our previous slide, that may you remember that here I can show you, whenever we have been discussed dielectric susceptibility, at that time we have been discussed that polarization susceptibility is nothing but polarization of atoms per molecules per unit volume, polarization of atoms or molecules per unit volume per unit applied electric field. That means Chi is your P, that is your polarization density or polarization of atoms or molecules per unit volume per unit applied electric field. In SI unit, epsilon 0 will be there, and in case of CGS unit, epsilon 0 is not to be there. So same thing we have been written over there, that Chi E equal to P by E, or that value is nothing but your N into alpha E, whatever I have been discussed right now. Okay. So here, hence complex dielectric constant, that means which is depends upon the frequency or relative permittivity, both are same, epsilon r function of omega of the dielectric material will be equal to 1 plus this much, that means 1 plus Chi E, that we have been proved in our previous topics. We found that dielectric constant is nothing but 1 plus Chi E. So here Chi E for electronic polarization we found this one, and we just substituted this value over here, right? Okay, now here you can see 1 here 1 plus the same term I have been written, I nothing changed over here, into I multiplied one term, that is your omega 0 square minus omega square minus I omega beta by omega 0 square minus omega square minus I omega beta. Okay. 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 So 1 plus, here you can see that n e square by m taken outside, and this is in the form of a plus b into a minus b. I can show you. Here you can see, take this one as your a, and this term is your b. So this will be a plus b, and this is your a minus b. That means a square minus b square we are going to write in the denominator. So omega 0 square minus omega square square plus omega square beta square. Here you can see beta b square. B square is nothing but is your I square omega square beta square. I square is nothing but minus 1 omega square beta square. So whenever we are going to consider a minus b, a square, a minus b in a plus b into a minus b, that is nothing but your a square minus b square. So a square is nothing but this term square. Here I have been written, and b square is nothing but this one, minus omega square beta square. So minus and this minus will be plus omega square beta square. Okay, and then here you can see this term by this one, a square minus b square term, then minus here minus I this n square written over here by m also written over here. So omega beta and divided by the so called your a square minus b square. Okay, okay. Simple calculation, you just write down in your note. One second. Okay, okay. So this figure is represents that number of atoms. Here I forgot to say one thing, that here you can see that suppose this is your unit volume. Okay, in this unit volume we can expect that more than one atom or molecules are present. So more than one single electron will be present inside this unit volume. So if n is the number of electrons present per unit volume, that means here you can see, if in this unit volume we are going to consider Ne is the number of atoms or molecules. Suppose we are going to go Ne, small n is the number of atoms and molecules per unit volume. Okay, so if this Ne will be increased, then obviously this n which is represents the number of electrons per unit volume also will be increased. Here I written because in our forthcoming classes, whenever we are going to discuss, these things will be required. Okay, so here you can uh, you just consider that if the atoms inside the unit volume is going to be increased, so obviously the number of electrons will be increased. Okay, okay. Now epsilon r omega will be equal to 1 plus this term is written as epsilon r prime omega minus this term is written as I is written there, this term is written as epsilon r double prime omega. Let this is your equation number 6. And this is nothing but called as your complex impedance, complex dielectric constant, or complex relative permittivity of the material. And here epsilon r prime omega, which epsilon prime omega represents a real part of this equation number 1, which is called as your dielectric constant of the material, actual dielectric constant of the material, and which is frequency dependent. Here you can see epsilon r prime is equal to omega 0 square, omega square. So obviously it is depends upon the frequency, applied SC frequency. Double prime term, this one is imaginary part of the equation number 6, which represents the dielectric loss part of the material, which is also frequency dependent. Okay, so I suggest you just remember the equation number 6, most important. Take the screenshot for your note. Now we are going to go for the variation of dielectric constant, that is your prime part, single prime and double prime part dielectric loss of a dielectric material with the frequency. So this is a typical graph of variation of dielectric constant or epsilon r prime, and this one, this blue one is belongs to epsilon r double prime, loss part of the dielectric material. Here I or same thing I have been written. The figure represents the variation of dielectric constant, that is your epsilon r prime omega, and loss, dielectric loss epsilon r double prime omega of the dielectric material with frequency. And here I mistakenly not written r, you just write okay r, and here also epsilon r double prime. From this graph, many electrical properties of dielectric material can be extracted. So here you can see the plateau region of real part of the dielectric constant, imaginary dielectric constant, represent the dielectric relaxation with the applied electric field. So this is the plateau region, and this is the dispersion region. This is the dispersion region of dielectric constant, real part of the dielectric constant, or epsilon r prime. This plateau region is represents the relaxation behavior. Relaxation behavior means this is the applied electric field, and this is the dipole. Suppose this is the dipole present, positive and negative part present in the material. So in this frequency range from here to here, the frequency with which AC has been applied on this dipole, the dipole polarized and depolarized accordingly. So here if I am going to consider positive half enters into the dielectric material, suppose this is the polarization, and when the negative half will be enters on this dielectric material, then exactly it will be altered. That means this will be negative and this will be positive. Okay, that means the dipoles which are present in the material exactly obey the frequency of the applied electric field. Only for that we found the plateau regions. You just remember this much, and extra you can study in your higher study. So plateau region represents the relaxation behavior, or that means we can say that the dipoles which are present inside the material obey the applied electric field frequency. And then after this frequency, it is not obey, so polarization not happens. And as dielectric polarization is easy, that means dipoles are obey the applied electric field. So here you can see a dipole is polarized along this way, this direction, again next half cycle this way. That means we can say that in this region, or in this frequency range, the dipole easily oriented, this is plus minus, again minus plus, minus plus, again plus minus, easily oriented. That means like this, it will be easily rotate inside the material. So if a perfect dynamics we can think inside a dielectric material, then loss, heat loss we can expect from the material. Hence whenever the EG polarization we found in that frequency range, also high dielectric loss, that means loss will be increase, and it will give a peak, and at which frequency the peak observed, that frequency is called as the omega 0, or called as your what, your resonance frequency, omega 0, where maximum loss observed for a dielectric material. So these are the two basic properties, electrical properties we can extract from this graph. So here I am going to remove these things, and you just take the screenshot for your note. So from these two basic electrical behaviors, the dielectric material is very much essential. These two basic electrical behavior of the dielectric material is very much essential for analysis of different type of electrical as well as electronic properties, such as capacitor, inductor, resonator, oscillator, absorber, etc. of a dielectric material for different type of applications towards sensors, actuators, transducers and memory devices, etc. Okay, so here we are going to stop our discussion. From the beginning I am going to show you the slides. You can take the screenshot for your note. This is the first slide, then this is your second slide, This is your third slide. This is your fourth one. Okay. So thank you so much for watching this video.